Hello everyone, welcome to my presentation. Today I would like to talk about our work, sparse convolutional networks for surface reconstruction from noisy point clouds. So let's have some general idea about the background. So as we all know, the neural network is powerful. It can be used to approximate any function. It also can be used to represent any digital signals as 2D images. So we also want to use the neural implicit field to represent 3D models. So implicit field is a common concept. So like the signed SDF, signed distance function, neural network can be used to approximate this function. Besides, occupancy value also can be used to represent shapes. So the previous work, occupancy networks, it also can be used to recover the 3D surface from the noisy point cloud. So it's generally use the neural network to take query points coordinate in space. This query point can be anywhere you like, but the network will output the occupancy value. So this network will take the query points coordinate and the extract feature vector from the input point cloud. So next work is about the convolutional occupancy network. It continues this idea. So, but what they did is they extract the convolutional feature from the noisy point cloud. So we also trying to use the convolutional feature since it includes the local information of the input point cloud. Okay, so let's talk about the motivation of our work. So we are also trying to reconstructing fine geometric details and have the capability to handle the noise input. So as I mentioned before, the convolutional feature includes the local information which help us to output the better surface. However, the convolution it consumes large computational resource, especially when it comes the 3D Vox grid, since there's another dimension compared to the 2D image. And there's another motivation is the sparse tensor, which is really helpful. So in the 3D space, actually there are many locations are empty, and the sparse tensor only stores the location where the features is non-zero, which saves tremendous space without information loss. Therefore, the contribution of our work is we can use self-model to reconstructing accurate 3D surface from noisy point clouds. So we build a neural implicit method based on sparse convolutions, where the features and the network calculation only focus on grid points close to the surface. This allows us to build significantly higher resolution 3D grids and reconstruct high-fidelity details. Furthermore, we also figure out a normalized weight interpolation approach, since as feature at nearby grid point to the query position may not exist due to the sparse nature. The third contribution of our work is the quantitative and the qualitative results demonstrate our method achieves state of art. So here is our pipeline. So as you can see, the rabbit is a noisy point cloud, and the way to reconstruct the smooth surface is you can query any point in the space, and you can get the occupancy value, and by querying many points in the space, we can use this occupancy value to define the surface of the 3D model. And we use the sparse res UNet to extract the feature. As you can see, we use the sparse convolution, which is the convolution only applied on the sparse tensor. So the location is not exist in the sparse tensor will be skipped. This help us to save lots of GPU memory and speed up the training. So we also can increase the resolution of the works grid to get the final detail of the final result. So here is the normalized sparse grid interpolation. Using a 2D sparse grid for illustration, point P is located outside of the sparse grid, but its enclosing grid cell contains the corners with the feature. So we use the interpolated feature to divide by the valued weight. So the weight of the Q11, Q11 is included. This helps us to get the smooth surface. So next is about the results. As you can see, our result is much better than other method, and on the right side is the quantitative results. Next is about the endorsing level. We also use our method to reconstruct the endorsing point cloud, which also got good results. We also test our model's capability to handling noise. As you can see, we test different level of the noise, and our method still got better results than others. And in terms of the efficiency, our model used the least GPU memory since the involvement of the sparse tensor and the sparse convolution. So that's it. Thank you for your time.